Greetings to all my tech heads out there in the KevTechify Nation. And if you're new here, welcome. In this episode, we're going to look at static and dynamic routing. We'll be discussing whether to choose static or dynamic routing evolution, dynamic routing protocol concepts, best path, and load balancing. This episode is part of my series on switching, routing, and wireless essentials for the CCNA. I'm Kevin here at KevTechify. Let's get this adventure started. You get the question, do we use static routes or do we use dynamic routes? And most companies, they actually use a combination of both of them. They're not exclusive to one or the other. And what we see is there's reasons to use one, there's reasons to use the other, and both of those reasons typically exist in a company. And so we get a combination of protocols and static routes in those. Now, static routes, they're typically used in networks when you want a default route going like to your service provider. Your service provider, they keep track of every network, every way to get to those networks on the entire network. Or sorry, not the network, but the internet. So think about those thousands and millions and possibly billions of networks out there. Now that we got IP version 6 out there also. Keeping track of all of those. You don't want to do that on your network. And so what we do is we set up a default route with a static route. If we don't match any of the networks that are underneath our control in our network, we're going to assume it's on the internet and we're going to send it to our internet service provider and let them route the traffic to the destination. If you got a route outside of your routing domain, you can use a static route there. Maybe you want to specify a certain path for your traffic to take. You want to go over an unmetered connection versus a metered connection as the network administrator. Maybe you want to stress test one of your devices on the network to see if there's a bottleneck or something like that. You want to direct traffic a certain way across your network. You're going to set up a static route to do that. Also, if you have stub networks where they have single connections, you're going to have to use some static routes there between those. Static routes are useful on smaller networks. Static routes are useful on smaller networks where there's only one path to the outside network would be an example here. They help you provide security in a larger network. You can direct traffic in a certain direction. You can make sure only certain traffic gets into a certain network. You only want certain people or certain devices to have connection to your HR network because you have all these federal regulations about controlling data and access like that. You set up static routes to make sure only certain people can get into that. Or where you're connecting into other networks would be another place where you use static networks. Dynamic networks you use those on networks consisting of more than a few routers. For me, if I have more than one device, I'm going to use a dynamic protocol. That way, the conversation happens between the routers. They determine which is the best event. And if I ever grow that network, it'll automatically take care of it. But a lot of people say up to about 4 or 5 routers, use static routes. For me, having to go in there and manually change everything, manually enter everything in on every router, that seems like a lot more work than just setting up a dynamic protocol. Dynamic protocols, they're scalable and they automatically determine the network. They have a conversation, they say, okay, this is the best way. Typically, we see dynamic routing protocols used when we have more than a few routers. Like I said, some people say 5 routers is a few routers. For me, anything more than 1 is a few routers. If you're having changes on your network, maybe you're upgrading your network, maybe there's a connection that's going up and down, whatever the reason, if there's changes on your network, that dynamic routing protocol will take care of fixing the routes. Also, if you're adding onto your network a dynamic protocol, it'll automatically adjust to it, it'll learn best paths, automatically calculate all of that information for you. So scalability is another reason you'd want to use a dynamic routing protocol. When you're comparing static routes and dynamic routing protocols, there's a couple things to consider. First one here is configuration complexity. If you're running a dynamic routing protocol, it doesn't matter the size of your network. If you're doing static routing, Every time you add in another device, you have to add in a lot more static routes. And not only to that new device, you have to go around to all your existing devices and add in those new static routes also. When your topology changes, a dynamic routing protocol, it'll automatically adjust to it. On a static routing, when you have a topology change, you as the administrator, you have to go in and make those changes. You have to go into every device that's affected by this routing change and update those static routes. Scalability, when you're adding stuff to a network, the dynamic routing protocol is suited to do that. It works for simple networks to complex networks. You can use a dynamic one. For static routing, only use it on simple networks. If you're going to use all static routing, a simple network. And like I said, some people say 5 routers and under use static routing. For me, anything more than 1 router, I'm using a dynamic routing protocol. When we're looking at security, security must be configured for a dynamic routing protocol. You want to make sure that only the correct people get into the correct areas to the correct information. You want to do that. So you have to configure that separately when you're using a dynamic routing protocol. Static routing, because the static route only allows certain traffic to certain destinations, you can control that. That's the security that's there. Resource usage. Dynamic routing protocol, it uses the CPU, it uses memory, it uses link bandwidth. It has to think about which is the best route, and then it sends it out. For static routing, there's no additional resources. It sees that static route, it matches it in a routing table, and it sends it out. There is no thinking about it at that point in time. And then when we look at path predictability, for dynamic routing, it depends on your topology and even what protocol you use. Some protocols will determine that going to the left is the best path. Some protocols will determine going to the right is the best path. It's up to the topology and the routing protocol used. Static routing, you as the administrator, you determine which is the best path. So you know exactly how your traffic is going to cross your network. I hope you're liking this episode on static and dynamic routing. If you have the time, please leave a comment and let me know what you think about static and dynamic routing. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. As dynamic routing protocol has matured, as it's grown up, it's went through growing pains. The first networks, ARPA network starts way back here in it's 1969. That was ARPA network. The first, or ARPANET, that's the first networks that connected 2 computers up. And so for several years, it was small enough that not everybody had it. And then finally, we needed to come up with how do we route between these? Because now we have redundant connections and stuff like that. We came up with EGP and IGRP. RIP version 1 was probably the first big routing protocol used out there. But when RIP version 1 was designed, we didn't think that we'd ever have thousands of networks. We didn't ever think that we'd grow as big as we did. And so for that time in 1988, RIP version 1 was great. It was the perfect thing. But as networks grew, there were limitations. RIP version 1 used only class full addressing. So you had to use a /8, /16, or /24. It matched in those class ranges. You couldn't use a /25 or 26. It always had to be a /24 address. It had a maximum of 15 networks it could learn. Why would we ever have more than 15 networks in the world? Well, things grew. And what come out 6 years later, 1994, RIP version 4. That is now classless, where we can use a /25 or a /26. And it got rid of that limited number of networks of 15. It raised it up to a much higher number. We see other protocols coming out here. OSPF version 2, version 3. We have ISIS in 1919. Then we have ISIS version 6. A lot of these earlier protocols only supported IP version 4. Why would we ever need more than the IP addresses in IP version 4? Whoever thought we would need that many, 4 billion addresses? Well, we do in today's world. Now we need more, so we have to have IP version 6 addresses. How do we route those? And so that's what some of the newer versions are. Plus, we just came up with newer, fancier, better algorithms, better ways to process it, more efficient ways to process data across our networks. As we look here, we can see that there are some evolutions growing up here. We have a lot of times what's referred to as interior protocols and exterior protocols. Interior protocols is what you run on the interior of your network. Exterior protocols is what you run on your edge of your networks to connect to somebody else's network. So this is where you would run this exterior gateway protocol on your edge router to connect to your internet service provider. And depending upon if you're using it internally or externally, determines that. Now, inside of these interior gateway protocols, there's 2 different types. We have the distance vector, and then we have the link state. The distance vector uses the distance, how far away something is, and that could be like how many routers, how many different networks you have to go through, and in what direction. What interface do I go out of? And so distance vector is concerned with either directly delivering it to the destination if it's a directly connected network, or getting it to the next device, so that way that device can then make a decision on how to route it. Link state, on the other hand, knows the state of every link in your network. It knows if it's up or down, it knows the speed, sometimes it even knows the congestion. How congested is it? How loaded is your CPU, depending upon which exact protocol it is. It knows everything about every connection between your routers on your network. Distance vector, concerned about getting it to the next router. Link state knows everything. So link state is more resource intensive. We have versions of IP version 4 and IP version 6 of each one. And notice, OSPF version 2 is IP version 4. OSPF version 3 is for IP version 6. BGP, Border Gateway Protocol, is typically about the only exterior gateway protocol being used in today's world. But I'm sure eventually there's going to be more protocols that are coming out, more efficient, able to handle the new IP version 6 addresses better. Dynamic routing protocol concepts. Now, dynamic routing protocol, it uses a set of different processes, algorithms, and messages. It exchanges routing information with other routers about how everything is built, how everything is connected, how everything is doing. And then it populates a routing table with best paths. Once again, we say best paths because it could have multiple paths to a destination network. We're going to choose the best one to put in our routing table. And so these routers exchange that information, build our routing table. Now, the purpose of these dynamic routing protocols is to discover the remote networks. They share information about the networks they're connected to the other routers. Those other routers then say, okay, I know about this network, but these 2 networks I don't know about. I'm going to enter it in and say I have to connect into the router, or I have to send it to the router that sent it to me. And so they keep track of all of that. They maintain the up-to-date routing information. So if a connection goes down or a new one comes online, you add a new router into your network. That dynamic routing protocol will take care of all of that. It chooses the best path. The quickest, the shortest, the fastest, depending upon the protocol, there's different things you can use to do that. And of course, when those new devices come online, we find that new best path with our dynamic routing protocols. How dynamic routing protocols figure out these things? There's several components to this. One is the data structures, one is the routing protocol messages, the third one is the algorithm. Data structures is how it stores this data. It stores it in a table, it stores it in a database. Typically, this information is kept in RAM. It loses power, you have to reboot it, it has to rebuild these tables. Then we have the routing protocol messages. Various types of messages to discover neighboring routers, exchange routing information, and different other tasks to learn and maintain accurate information about the conditions of our network and how to get there. And then finally, there's the algorithm. The algorithm is a list of steps that help determine the best path. Routing protocols use the algorithms for facilitating the routing information and best path. Now, to determine the best path or the route, once we've done that, and so we use all three of those components to determine the best path, that best path is then offered to the routing table. So the protocol figures out, okay, this is the best path. Then I'm going to offer it to the routing table. The routing table will then look and say the administrative distance. Do I trust this path you gave me more than I trust the other route I know about? If I don't have another route, I put it in there. But if I do, I have to look at the administrative distance between those two paths. And the one with the lower administrative distance is the one I'm going to put in the routing table because I trust that one more. To determine the best path, typically there's a value or what we call a metric that each routing protocol calculates. It can be looking at bandwidth or hops or a combination of everything. They use weighted values, but it's some sort of quantitative value, a number. It breaks it down to a number. And then once we have this number, the routing protocol can say, okay, which is the best path? Because you may have multiple paths to the destination. The routing protocol, based upon its metrics, will say, okay, this is the best path. Then that best path is presented to the routing table. The routing table looks at the administrative distances, and the lower administrative distance is the path that's entered into the routing table. Here are three different dynamic routing protocols: RIP, OSPF, and EIGRP. RIP is the oldest one out there. Their metric hop is their metric is what we call a hop count. Every time you go through a router, it counts as another hop. Every time you change networks, it counts as another hop. And how this worked was, the further away it was, the more networks you had to go through, the higher the metric was. And so you want the lowest possible metric. As mentioned earlier, the problem with RIP was 15 hops were allowed. So that's why a lot of people don't use it. RIP is very simple to implement. If you have a small network, you may want to do that, but realistically, I wouldn't, in a production environment, implement RIP. OSPF is the one I would implement. Open shortest path first. The metric is what we call cost, and that's the cumulative bandwidth. And so, faster the link, and there's a table, and if it's a fast Ethernet, a 10100 connection, it's assigned this value. And so every time it goes from one device to another device, it looks at that connection speed and it gives you a value. The faster that connection is, the lower that number. And then it adds up all of those numbers. And then finally, each path has its number, and the lowest number is the best path for OSPF. So it looks at the speeds. And then finally, we have EIGRP, Enhanced Interior Gateway Routing Protocol. This metric is based on slowest bandwidth and delay values. So it looks at the path to the final destination network, and it looks at the slowest bandwidth. So is it just an Ethernet connection with a maximum speed of 10 megs? Is it a fast Ethernet with 100 megs? Do you have all gig all the way through to your destination? It looks at that and it assigns value. You could include other parts into the calculation for EIGRP. You could look at load of the processor, load of the connections, how congested is it? We can look at reliability. Is it a reliable connection or is it an unreliable connection? And it does its calculation based upon that. It is possible to load balance between two connections on your network. What happens is you have to have equal cost metrics. Forwarding uses both paths equally, and so it'll send out one packet on one port, one packet on another, but they have to be equal. This is known as equal cost load balancing. They have to have the equal cost in their metrics. In their metrics. The metrics, the Dynamic routing protocol does its calculations, and it came up, hey, these two paths have exactly the same number. They're the best way to get there, but there just happens to be two. What we're going to do is we're going to connect between them. The routing table, it contains a single destination network, multiple exit interfaces, one for each of the equal cost paths. Now, when you do get this configured, it will increase effectiveness, it will increase your throughput, it'll increase your performance. It'll allow you to use both of those connections equally. Now, equal cost load balancing is implemented. If you're using dynamic routing protocols, it'll automatically do it if it calculates out the two routes to be equal. Now, if you're using static routes, you have to make sure that you set the two static routes to different next hop routers. It needs to understand that, hey, one route goes to this router, one route goes to this router. And when it's the static route, it's the identical static route, but one goes to one router, one goes to the other route, it will do that equal cost load balancing between that. EIGRP of the protocols we talked about is a little bit special. What we can do with EIGRP is unequal cost load balancing. Notice it's the here, so unequal. All the other ones were equal cost load balancing, where they had to be identical. EIGRP, you can use unequal cost load balancing. So even though there's two paths to the destination, they have different cost numbers, they have different metrics they're set up. You can still set up load balancing between them. It was my pleasure to provide you with this wonderful episode on static and dynamic routing. If you like this episode and you got value out of it, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All my socials and contact information are on my website, KevTechify.com. There you can find out how to get all these episodes in video and podcast form. In the upper right is my playlist for my series on switching, routing, and wireless essentials for the CCNA. Thank you so much for watching this episode on my series on switching, routing, and wireless essentials for the CCNA. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.